So in this episode, I'm not going to re-implement the game of life, but I'm going to take our previous solution and improve on it by adding configurability for rules and for the topology of the cells. So while editing the previous episode, I noticed one typo here, and I'm going to do this rename. For Game of Life, we had the rule that 3 neighbors spawns and 2 or 3 neighbors keeps a cell alive. This is fairly arbitrary, and there are alternative rules. For example, we could say that 3 or 6 neighbors spawn a cell and 2 or 3 neighbors make it stay alive. This alternative is called high life, and it's one of the most famous alternatives of Game of Life. So to support these alternative rules, we are going to modify our code. To implement the alternative rules, we only have to change this single function here, because this is all the rules. The only problem with this solution here is that this kind of combines the stay alive rule with the spawning rule, because this part is about both and this part is only about the stay alive rule. So I'm going to refactor this a bit, and instead of what we have there, I'm going to have an if statement that specifies if we are talking about a stay alive case or a spawning case, and for both I'm going to return something like this. I'm gonna list the number of neighbors that indicates stay alive, and I'm just going to use the includes here. And similarly here with the simple 3 and say includes count. And after this simple refactor, just checking if all the tests are run, yeah. With this simple refactor, we are really close to solving this problem. We just have to write a couple of tests and fix them. So we specify that single neighbor stay alive rule works. And then I'm just going to write it so I'm just going to create a new game because I want to pass in the alternative rules via the constructor. And here we have the stay alive rule, and then I will have a game spawn the cell 00 and the cell 01, do an evolve, and expect alive for this cell 00. And of course now this doesn't work because we need the constructor to take the stay alive rules and just make this a field. And now I just have to put this in here. And of course it fixes this last test but breaks a couple of tests because we also need to specify the default value, which is the 2 and 3 array. Then we also should write a test for the spawning rule, so the single neighbor spawn rule works. I don't need this here. Now I have to pass in both the stay alive rule and the spawning rule. and of course this fails. I come in here, add the spawning rule here, make it field, use it in the should be alive function. Again, last test is fixed, but all other tests break, so I will also have to add the default here. Now, this seems like we are done, but actually we are not, because for the spawning it doesn't make sense to allow 0 in the array, but for the stay alive rule it actually makes sense to allow cells that have 0 neighbors to stay alive. The reason it doesn't make sense for the spawning rule is because then every cell would suddenly become alive, and that's just not possible with this particular implementation. So I will change this to 0, I will remove one neighbor here, and then this should also work. And the reason that doesn't work is because the last time when we implemented the game of life, we actually in this step we had the assumption that every cell that is alive had a neighbor in the previous generation. This actually breaks down when we have the 0 stay alive rule. The way to fix this is that we are going to add the cell itself to the array that is being flat mapped here, and then basically we also include the cells when checking the previous live cells, and that fixes this one as well. Another interesting variation on the game of life is when we use hexagonal cells, where each cell has exactly 6 neighbors. The question most people ask when they see the problem for the first time is how can we define the coordinates? And actually it's really simple for the y coordinate, because we can just pick one row as our center row that will be code 0, and we will number the rest of the rows from there. It's also simple to find an x coordinate within a row, because we can find a central cell that will be or 0 and number the cells from there. The trick is how can we define the 0 cell on each row consistently. One solution people use is to use fractional coordinates for the odd numbered rows, or another solution would be to pick 2 vertical lines separately for odd and even numbered rows. But actually the simplest solution is to find the diagonal and use those cells as or 0, 0 cells. The advantage of this solution is that it's really easy to calculate the neighbors. For example, the 0, 0 cell has these neighbors, and these are exactly the same neighbors as a square cell has, except 2 neighbors are missing. If we wanted to make this permanently a hexagonal world, we would just have to remove this line and this line from the code. But we actually want to make this configurable, and the easiest way to make it configurable is by just creating 2 separate kinds of cells. So we are going to have a hexagonal cell, and this will be almost the same as this one, just without these 2 neighbors. I'm going to write tests that hexagonal cell has neighbors. Actually, let's first write the case when we convert it to a string. So the said that hexagonal cell can be converted to string. And then I'm going to just create a cell, new hexagonal cell, 0, 0, and then cell to string. We expect this to be and we could just write 0 0 here, but if we do that, then it has the same string representation as regular cells. I just don't want that, so I will just add a prefix here. So this test fails, and we already have a toString method because all objects have one, but we want that to be different, so we actually need to have a constructor to have the x and y coordinates come in, and then toString return, and first I'm just going to return hex 0 0. So we need to write one more test, and instead of just copying and pasting this, I will actually use the same trick as before for data provider. And in this data provider, I will actually need two parameters. One is the cell, and the other one is going to be the stringified version, string representation, like this. I actually forgot to add one more parentheses there, and let's move this inside there. And basically what I did there, I disassemble an array, so each case is going to be an array of two elements. One is the cell itself, and the other one is the string representation of the cell. Actually, I don't need that line anymore, and here I can just write string representation. And I can also write something like, let's convert this into template string, and I will just include the string representation here. Okay, so that still works. And now I just add one more test with another set of coordinates. Which of course breaks, and I go back to the hexagonal cell and just include, well, I first need to convert these into fields, and this one too, and just use it in here, and this is why. Actually have a typo here. Okay, now we can write the tests for the neighbors. So we specify that hexagonal cell has neighbors, and like this is the same thing as before. We just have to replicate the same code as what we have here, just with these two lines removed. So let's write one of these tests quickly. So we create a cell, new hexagonal cell 0 0, and we say we expect the cell dot neighbors to equal, and then a list of cells, and what are the cells that we need? Well, we need well, not the -1 but we need the -1 0 and the -1 1, and also the 0 -1 and the 0 1, and then 1 -1, and finally 1, 0. These are the cells that we need, and these should be hexagonal cells. This is a failing test. We just take this here, copy it, paste it in here, remove this line and this line, and make this a hexagonal cell. And done. So we should actually write a test with a hexagonal cell just to prove that this works. So I'm going to specify that hexagonal cell with, actually I'm going to add these, and hexagonal cell with non-neighbor -1, -1, and 1, 1 dies, because these two are neighbors with the normal game of life, but not in the hexagonal game of life. So when I create, when I take spawn these cells with hexagonal cells, not regular cells, and then evolve, then we should expect that hexagonal cell 0, 0. And that actually passes because we already had everything that we needed. Finally, let's do a multi-dimensional world. So we have currently the 2-dimensional cell, and we could generalize this to be an n-dimensional cell. The way I do that is by creating a new class again called multi-dimensional cell, and this multi-dimensional cell will represent any dimension with regular grid. So to implement the multi-dimensional case, we are going to write a test that specifies that multi-dimensional cell has string representation. And here I'm actually not going to write a proper data provider, because this is going to be a really simple test. I will just include multiple assertions in the same test. It's not strictly legal, but in this case these are simple enough tests that I won't care about it. So new multi-dimensional cell, I will just pass in the coordinates, and we expect this toString method for this to be equal to just a 0, like this. Multi-dimensional cell is not defined, so we are going to create that class with coordinates as the parameter, and then we actually need to override the toString method. And in this case I will just return whatever, like this. Okay, now go back here, and as I said, I'm going to just add multiple asserts here. Okay, now we can create this field here and make this a template string, and just add dot coordinates 0. Okay, now let's do an example with multiple dimensions, so 4 and 9 for example. That fails. So then I come here, and instead of this I'm going to say dot join on commas, and that's it. So we have the string method, toString method done, and then we can specify that multi-dimensional cell 0 has neighbors. So, and now I can say that I expect new multi-dimensional cell with a single 0 coordinate dot neighbors to equal, and then here is the array that we want to equal new multi-dimensional cell -1 and a new multi-dimensional cell +1. Okay, so this is not a function. Let's create it. Now it's not returning what we expect, so let's do whatever is necessary. 0, sorry, -1 and 1. And that doesn't work because we actually should pass in arrays here. Next thing that we need to do, again, not gonna well, let's write one more expect here, and I might actually turn this, no, I'm gonna turn it into a data provider, because this one is a bit more complicated. I don't want to make it very involved, so I will just make this, replace this occurrence only with the cell, and here with neighbors, and then I will write make them part of an array. This is going to be the first element of that array, and this is going to be the second element of that array, like this. And I'm going to do a for each with cell and neighbors. Move the test into the for each and remove these two lines. Oh, this is a, so this is the result instead of, so that to avoid the name clash. Neighbors is not a function. Oh, I see the problem. So I should decompose the array here, and that was the problem. I had an array of the first parameter and the second parameter and didn't add two square brackets there. Okay, now that it's decomposed, it works. And I will also turn this into template string, and here just add cell. Okay, so now we have a refactor test, and I can add one more test case. like this, and this case is going to be for 5, and then here 4, and then 6, and then we can go back here, and instead of just specifying these, I could say this dot coordinates 0 minus 1, and this dot coordinates 0 plus 1. So this works. But now we have to find a way to extend this into multiple dimensions. But before we do that, I want to do a bit of refactoring. Here we create the multi-dimensional cell over and over again. So why don't we just do that as a map? See, okay. And then I can remove this part. It's a bit cleaner that way. And the other thing that I will do is I will actually add in one more cell here and filter it out. The reason I do that is because here when we start building the several dimensions, it will be really inconvenient to have that missing center cell. So what we are going to do is I'm going to build up the 3x3 box and then just remove that one cell from the middle. And this filter here is going to do that for us. I'm going to say that if c.toString doesn't equal this dot toString, in that case we are going to keep the cell in the map. And that, as you can see, for the existing test, that's already works. Okay, now we have the first complex case. These two were fairly simple, but this last one is going to be actually really challenging to implement. Because then now we have two different coordinates, and I need to find a way to actually list those. So I have to write something like 4 and 8 is the first neighbor, and then we need the 9 and the 10, and we need more of these with the 5s, and also with the 6, and just remove the 5, 9 because that's the center cell. So this is the test that we need to write, and this is what we want to get. Okay, so let's go back there, and now we actually should do, so what the way I'm going to do is I will start out with the 0-dimensional case, and with each dimension I will just generate the new dimensional, the 1+ dimensional box from the previous one. And this is not really easy, so I'm going to just do console log here and keep running this one test that that I have, and look at the results. So the 0-dimensional case is this: we have the single cell in a 0-dimensional case that is the center and has 0 coordinates, and then I want to generate this from it. And the way I can do that is I will just start out with a single 0 cell here, just to show you what's going on. And I will do a reduce that starts out with this special case of 0 dimensions, and in there I will do like these are going to be the coordinates, like this is a 1-dimensional case, and I will have the neighbors from a previous dimension, and the new coordinate. And from that, I need to generate the new case. And what I could do is I could just say, I'm going to take all the neighbors and turn this. And for each of the neighbors, I will do a map. And one thing that I could do is just take the coordinates of the neighbor. These are the coordinates of the neighbor, and see. Just disassemble it into this array and just add the one extra coordinate. What this would do is just add that one middle cell. But we actually need two more, the -1 and the +1 case. But if I were to do this like this, like listing these three cases in an array like this, the problem would be that we get like this nested thing that isn't what we really need. And the way we can forego that is by using a flat map. And now, if I add one more 0 here, then we actually get the neighbors of the 0, 0 cell, which is really nice. So that means that now if I just replace this with these coordinates, then we have the result that we want. And what I'm going to do is I'm going to take this whole thing here, cut it out of the console log, and replace this array with it. And that's it. We are done. It's a little tricky, and it's not such a readable code as the original solution. Like here it was really readable what we are doing. This actually requires some thinking to understand, but I kind of like this solution because it shows how powerful reducing flat map can be. And maybe I can also do a bit of remove braces here and also here, and that's it. This is the final solution. So just to make sure that our code actually works correctly with the multidimensional cells too, I'm actually going to add one more final test, and that is going to specify that, and this test will pass right away. It's just a final integration test or something like that. So we specified that multi-dimensional cell spawning works, and basically this is going to be a very simple test where we have a game. Actually, we already have the game. Let's game spawn a new multi-dimensional cell with 1, 0, 0 and 0, 1, 0 and 0, 0, 1. So these are three different neighbors of 0, 0, 0 in three different dimensions. And then we do the game evolve, and we expect a live new multi-dimensional cell 0, 0, 0, and this should pass. And it doesn't. Yes, because I again forgot to add the square braces here and here. Now it works. As always, you can find the final code in the description as a gist. And don't forget to like and subscribe. See you next time.